It's about time to get even one dimension more. Heat conduction in 2D. So we're talking about a temperature distribution that depends on time, on x, and as a premiere, on y. One way for visualizing this is a movie. Each frame of the movie depicts the temperature distribution in x and y at that precise instant of time. Then we come to the next frame of the movie, which shows us the next distribution in x and y, and so on and so on. And what we expect to see is diffusion. If there's only one hotspot at the beginning, it should gradually dilute over time. The heat equation in 2 dimensions does not contain any surprise. The partial derivative of the temperature with respect to time equals thermal diffusivity times the second derivative of the temperature with respect to x plus the second derivative of temperature with respect to y. Note aside, this expression is often called the Laplace operator applied to t. Don't confuse this triangle with the delta. It's also often called the Laplacian. You can imagine the Laplace operator to measure something like the bend of a surface in 2 dimensions. And there's a very simple finite difference scheme for that differential equation as well. Now we're looking at one point at the current time and the current values left and right, below and above, to compute the next value at that central position. That next value is the temperature after one time step at x and y. And we can spell out our estimate. This is the value before times 0 x and y plus the time step times the diffusivity divided by the spatial step size squared. And now we get lots of terms. The values of our function to the left, to the right, below and above, all at time 0. To the left, x minus delta x. To the right, x plus delta x. Below, y minus delta x. And above, y plus delta x. Hopefully it's not overly confusing that I'm using delta x to also denote the increment of y. Now that we've covered the outer point, the inner point remains. In 1 dimension, we have to subtract twice the value of the inner point. In 2 dimensions, we have to subtract 4 times its value. It's easy to see that this has to be a factor of 4. Imagine that it's equal to 100 Kelvin everywhere. Then we get 100 plus 100 plus plus makes 400. We subtract 4 times 100, so we get 0. The new temperature will be the old temperature, as it has to be. There's nothing that could be smoothed out if the temperature is already constant in space. This factor of 4 also hints at what's going to happen with instability. We have to be even more picky about the step size. It can only be half as large as in the 1-dimensional case. And the ugly artifacts that we are going to see close to instability are checkerboard patterns.